Okay, let's have a look at bond energies, or when we break those bonds and reform those bonds, bond enthalpy, and how we use this bond enthalpy to predict the change in enthalpy for chemical reactions. So bond enthalpy is the enthalpy change on breaking 1 mole of a particular chemical bond to produce electrically neutral fragments for that particular combination. So if we've got a carbon-to-carbon single bond, the energy that we need to put into it to break that bond to give us our 2 carbon atoms is known as our bond enthalpy. And we should notice that we always put energy in, so it's an endothermic process. So for this, our delta H value will always be positive. Now why is this useful? Well, first of all, we can calculate change of enthalpy for reactions, but it can also be useful because it can indicate the stability of molecules as they sit at room temperature. So for instance, hydrogen in its diatomic form has a single bond between the hydrogens. To break this bond will require 432 kilojoules per mole of hydrogen. On the other hand, nitrogen with its triple bond requires 941 kilojoules per mole. So much higher for the nitrogen, that triple bond. Now nitrogen is an extremely stable molecule at room temperature. In fact, to break down that nitrogen has got to go through a series of steps to break down each of these particular bonds. Hydrogen, on the other hand, has the one single bond, and as we see, it's relatively easy to break down. Now this is the breakdown process. If we want to form bonds, energy is always released. And we must get this because we get the conservation of energy. So if we're forming bonds, and that being an energetic process, this is an exothermic process, so our delta H, or change in enthalpy, will always be negative. So let's apply this information to a problem. So we're going to use our bond enthalpies, or bond energies, to calculate the heat for a reaction. So we have a reaction, we've got 2 moles of hydrogen in its gaseous form, combining with 1 mole of oxygen in its gaseous form, to give us 2 moles of water in its gaseous form. So if we break this down into its bond, or we represent them in terms of bonds, we have 2 molecules of hydrogen, each single bonded, and to break each bond in those hydrogen molecules will require 432 kilojoules. So we've got 2 lots of it. We've got to break the 2 lots of bonds. Our oxygen exists as oxygen double bonded with oxygen, so it's going to require 495 kilojoules per mole to break down. Now there's only 1 mole of this, so we only need to take into account the 495. That's our reactants. Our products, on the other hand, we've got 2 moles of water. So if we enlarge this or draw it out, we've got a hydrogen bonded to an oxygen, another hydrogen to an oxygen, a 3rd one, and a 4th one. So we've got 4 OH bonds. And each one of these bonds will require 467 kilojoules to break. So how do we actually calculate the heat of reaction for this particular reaction? Well, we need to find the sum of the bond enthalpies in the reactants, and then we subtract the sum of the bond enthalpies in the products. And if we think about this, if this one is higher, or sorry, our reactants is higher than our products, then our reaction is going to be endothermic. On the other hand, if our reaction or our bond enthalpies for the products is higher than the reactants, then the process is going to be exothermic. So let's plug in some numbers. On the left-hand side, we've got our 2 moles of the 432. We've got 1 mole of the 495. We subtract our products, so we've got 4 times this particular bond, the OH bond. So if we calculate this, we find that we get a value of minus 509 kilojoules per mole. So this process is an exothermic process. Now this is a theoretical value based on bond energies. The measured value, or the measured accepted value for this particular reaction is 483.6 kilojoules per mole. So why do we get this difference? Well, it actually turns out that these bond energies are actually average bond energies taken over a number of compounds. So a hydrogen-hydrogen bond will only exist with this particular molecule. An oxygen-oxygen double bond will only exist as this particular molecule, although there are rare instances where we can get others. But the OH bond is quite a common bond in many different molecules. So in water, it will have a certain bond enthalpy, but if we put it into an alcohol group, it'll be a slightly different measurement as well. So this particular number here, the 467 kilojoules per mole, is an average of all the different types of compounds that contain an OH bond. And that's why we see this slight discrepancy in our heat of reaction.